Hi everybody, it's Mr. Piety back with you for the last session of IB Chemistry Learning for the summer 2020. We have one lesson left to finish for this topic, and that's line spectra. We're going to talk about bright line spectra and continuous line spectra. So let's do it. Let's start, like we start all of our lessons, where we left off last time, and that's talking about the structure of the periodic table as it relates to electron configuration. So let's look at this multiple choice question here. An element in group 2, which statement about the atomic structure and the periodic table are correct? An element in group 2 has 2 electrons in its valence or outer energy level. That makes sense to me because a group is the vertical column going down, and this has 1 valence electron, this has 2, 3, 4, 5, 6, 7, 8, and that makes sense. I like this one, that's a true statement. An element in period 3 has 3 electrons in its energy level. Now wait a minute, a period, well, that is a horizontal row, and so that tells us what energy level we're at, but it doesn't tell us how many electrons are in that energy level. So that's no good question there, or statement, I should say. Do not agree with that. The element in group 2, period 3, has an atomic number of 12. Well, let's see here. I'm going to clean this up. So this is group 1, group 2. So we're talking about something in this column, and then in period 3, this is period 1, period 2, period 3, and there's the atomic number there. I like that. So question or statements 1 and 3 are correct, which means B is the correct choice. Great, we're all caught up with electron configuration, structure of the atom, relating things about the element to the periodic table. That's what we've done before. What we want to do now, excuse me, my allergies are bothering me today, is we want to talk about the electrons again. We want to explain the difference between continuous line spectra and bright line spectra. And we want to explain that electrons move up in energy when light is absorbed and down in energy when light is emitted. So let's think about what we've talked about in the last several lessons. Well, we learned about the proton, the neutron, and the electron. And we learned that the proton and neutron live in the nucleus, and the electron lives outside in these energy levels. And we can describe those energy levels with electron configuration. What we want to do now is understand how light that we see relates to the movement of electrons. It's pretty fascinating. And again, it comes back to the Bohr model. Okay, let's talk for a second about the electromagnetic spectrum and about waves in general. Whether you're in a chemistry class, whether you're at the beach surfing, I hope some of you made it to the beach this crazy summer, or whether you're listening to radios, you're on your computer, listening to music, waves, right? Waves are everywhere. And so it makes sense in a way that waves would be reflected in atoms. Think about that for a second. Like waves are ubiquitous in nature, which means they're everywhere. So we want to understand how are waves reflected in atoms. And to do that, we need to talk a little bit about the electromagnetic spectrum. So for those of you who took chemistry last year, you know a little bit about the physics last year. And actually, if you took chemistry, we touched on this a little bit. Let's just make a general statement. Waves have energy. And the shorter the frequency, which is what you're looking at here, the greater the energy. And that's true whether it's a jump rope or ripples at a pond. We just had a hurricane go through the eastern seaboard, and that produced some strong waves on the eastern seaboard. Well, the greater the frequency of the waves, the more energy associated with them. The same thing is true with the electromagnetic spectrum. These two waves are what we call mechanical waves. The interesting thing about light is that it's part of the electromagnetic spectrum. And what does that mean? Well, it means that if we break the word down, often in science, if you're not sure what something's talking about, try to break the word down. And it's a terrible line. Let me fix that line a little bit if I can. There we go. Trying to get my hand back. There we go. Electro, there's some electricity involved. Magnet, oh, there's a magnet. So it turns out that when you have an electric field, you also have a magnetic field. And the converse is true too. When you have a magnetic field, you have an electric field. Physicists about 200 years ago figured that out. Pretty amazing discovery, really important to us. But what do we need to know about the electromagnetic spectrum? Well, we need to know that there are different regions of the electromagnetic spectrum that are associated with different amounts of energy. And so this is a diagram that many of you might have seen before. And it goes all the way from very high energy, short wavelength, to low energy, long wavelength. So the radio waves, if you listen to the radio in the car and it's not, well, even if it's satellite radio waves, you're getting very, very low energy waves that can travel a long distance. On the other hand, if you break a bone, like I broke this wrist a couple, 3 months ago, and I had to get x-rays. And so I got a very short burst of high energy radiation, and it took a picture of my bones. Okay, so the different regions in the electromagnetic spectrum that we kind of care about are radio waves, microwaves, infrared waves, visible light. I'm going to stop there for a moment. If you look here at this picture, that is a zoom in of the visible spectrum. So if you say, hey, is visible light strong or high energy light? Yeah, it kind of is. I mean, if you compare it to infrared or radio waves, like visible light can burn you. X-rays, much higher in energy. So we're going from low energy on this list to higher energy. Ultraviolet, the next higher up. X-rays, higher than that. And then gamma rays. I think I pointed to this before. This is a gamma. This is the Greek symbol for gamma. Okay, so different types of electromagnetic radiation can be classified according to their energy, wavelength, and frequency. These next few slides would apply to physics or chemistry. They overlap. Okay, let's define a couple of things. The wavelength, which is given the symbol lambda, is the distance between two crests of an oscillating wave. An oscillating wave just means going back and forth, right? So my pen here, sorry, it's hard to see, is oscillating. Many things in nature oscillate. The sun coming up and going down, the earth oscillates around the sun, all kinds of things, tides, right? So, and it has units of meters. That's it's a distance. The frequency, which this is the Greek symbol nu, is the number of waves that pass a point in 1 second. So it has units of hertz or per second. Hertz was a scientist. If you're a scientist and you figure something out, you might get a unit named after you. So, okay, frequency and wavelength, they are related. The energy of the electromagnetic spectrum depends on its frequency. A higher frequency means a higher energy and vice versa. And it has units of joules, right? So we're going to introduce an equation here which says energy is equal to h nu. Well, we learned what nu is. That's the frequency of light, how fast the light is translating past a point. The next thing that we want to define is this symbol H, and that is what's called Planck's constant. It's a value that you'll be given all the time. It's the energy associated with one photon of light. Okay? You don't need to really remember that a whole lot. We'll talk about it some more. But let's look at this image here. It's telling us something. It says, hey, well, I'm kind of looking at a Bohr model here. This is the first period on the periodic table, the second, the third. And as this electron goes from the second energy level to the first energy level, it's emitting some light that has this energy, right? So there's a relationship between the energy of an electron, or excuse me, of a photon of light and the movement of an electron in an atom. Like, to me, that's one of those things I'm just like, whoa, okay, that's kind of cool. I didn't know that. Now I do. Okay, let's talk a little bit more about the electromagnetic spectrum, and let's try to relate wavelength to frequency. And we can do that with another equation, and that is the speed of light, which is a constant. And anytime in science, when you have a constant, it's a good thing, because that means it doesn't change, and we can make observations around that constant. This is a constant here, which allows us to relate energy to frequency, even though I have frequency spelled incorrectly. I know one of you guys caught that. Okay, this one is saying that the speed of light, which is c, you don't have to memorize these symbols. You will come to know them. The speed of light is equal to the wavelength times the frequency. Okay, well, that's an interesting observation, because it presents a relationship to us that we would like to be familiar with. When we're graphing stuff, there's usually two relationships that we care about. One is a direct relationship, and that's actually this relationship here, which says if the frequency gets bigger, the energy gets bigger, right? That's the direct relationship. This one here is relating wavelength and frequency, and it says that as the wavelength gets bigger, the frequency gets smaller. As the wavelength gets smaller, the frequency gets larger. So that's an interesting thing. This is called an inverse relationship right here, because it has this appearance. We'll talk more about inverse and direct, but anytime we can identify those two relationships, that's a good thing, because you could see it in other things too. Okay. Woo-wee. Let's go back to the Bohr model. The Bohr model of the atom was really great at making the observation of how electrons interact with light. Let me just talk for a second about Niels Bohr, because he's a pretty cool cat. He was an ambulance driver in World War I. He volunteered for that. And he just stop, think about that for a minute. Like, he was not interested in hurting people. He wanted to help people. And he went to about the most dangerous place you could find to help people. So in my book, good on you, Niels Bohr. He also was a pretty good soccer player. He played for the Danish soccer team. Now in Europe, football or soccer is the national sport of all those countries. So if you are representing your country, that's pretty amazing. That's like playing basketball for the USA in the Olympics. You got to be pretty good. So the guy was super brave. He was a great athlete. And oh yeah, that's right, he's a brilliant person. So Niels Bohr, we salute you. Let's talk about how Niels Bohr's model of the atom is important to us. Ignore all this stuff over here. This is just me making a flip chart and not cleaning it up. I apologize for that. There we go. So let's see here. Line spectra. What does that mean? Let's talk about that for a minute. One of the primary sources of information on the arrangement of electrons in an atom was the study of line spectra. What does that mean? Okay, well, basically what Niels Bohr did, people knew before they even knew about the structure of the atom, they knew that the sun was mostly hydrogen and helium. And that's pretty amazing that they figured that out. And so what Bohr did, which was amazing, is he took a glass tube and he filled it with hydrogen. And then he did what any curious person would do. He charged it with electricity. He plugged it into an electrical source. They didn't have outlets back then. And that made the electrons glow. These were now, this is now plasma. And then he had a very narrow slit. And so what was coming out of this slit was a very narrow beam of just light coming from hydrogen. And then he passed that light through a prism. People hundreds of years before Niels Bohr knew that when you exposed visible or white light to a prism, it would separate into a rainbow. And that's what you see when you see a rainbow in the sky. It's nature's prism, that's water. And when he did that, he got kind of an interesting observation here. He got on some fluorescent paper distinct lines, bright lines. Excuse me. Okay. And that gave him, because they knew already that the sun was mostly made of hydrogen. And so when they passed this light through it, they were able to make this observation. I got a little bit ahead of myself here. So now let me show you a couple other bright line spectra here and a continuous. This is the rainbow that we see from white light, because white light coming from the sun is a mixture of not just hydrogen and helium, but many other gases. Okay, so it's important to note that different elements have different characteristic line spectra, similar to the way that people have different fingerprints. So this was amazing from Niels Bohr's perspective, because he was able to make the connection between the hydrogen in this glass tube here and the hydrogen on the sun and the light that it was producing, either emitting or absorbing. And this is helium, a little bit hard to see on my screen, but there's more lines here. And this is iron, which has many, many, many more lines. It's much more complex. Pause the video for a second and try to answer for yourself, why might that be that this is way more complex than hydrogen or helium? Iron has many more electrons in it. And so this movement that we are seeing, which is responsible for light that we see, there's a lot more electrons moving. Okay. All right, so let's keep going here. The electromagnetic spectrum, I think we've looked at this one already. Let's see here. Okay, that was what I did, is I combined two lessons kind of into one. We got about 10 more slides to go. Pause the video if you want, take a break. We're going to come back and we're going to answer these warm-up questions, which are trying to kind of connect everything that we've done. And then we're going to finish our discussion of bright line spectra. Okay. All right, so here's some warm-up questions. Consider the composition of the species W, X, Y, and Z below. Which species is an anion? Well, an anion is an ion. A cation is a positively charged ion. And how do I know that? It's got the plus sign right in it there. An anion, on the other hand, well, that's a negative ion. But that means it's got more electrons than protons. Okay, so we need to find a species that has more electrons than protons. 9, 10, could be that one. 11, 11, it can't be that one. 12, 12, can't be that one. 13 and 10, this has fewer, so it can't be this one either. So the answer is W. Use the following choices to answer questions 2 to 5 below. Which one corresponds to a noble gas? Well, a noble gas has a completed octet. It should have an energy level that has 8 electrons in it. This only has 3. This has 1. This has 2. This has 2 right there. This is this is nothing. This only has 1. This one has 8. So this one is a noble gas, and I'll give you a bonus if you could tell me what it is. That's right. It's neon. Represents an impossible electron configuration. Well, that's D, because I looked at that. We can only have something that's P6. We can't have P7. That's not correct. The ground state for magnesium. Now, magnesium is atomic number 12. So it's going to be 1s2, 2s2, oh, let me fix that, 2s2, 2p6, 3s2. Let's find that. 1s2, 2s2, 3. There we go. That looks like it's C. Represents an atom in an excited state. Let's see here. That's this one right here by process of elimination, but also because this, if it was a ground state, would be 1s2, 2s1. It would be describing lithium. Okay. I think I have a couple more questions for you here. Maybe not. All right, so what are our objectives here? Explain the difference between continuous and line spectra. Explain when electrons move up in energy when light is absorbed and down when light is emitted. That's an important idea. Let's see here. Okay. Now, if you were taking physics, you're gonna learn a lot more about this. For IB chemistry, what do we need to know? What part of this spectrum do we have to understand? Well, we want to know what's happening in the UV, in the visible, and in the infrared. So, okay. Now, you have to be careful when you're looking at these spectra. Sometimes they will go left to right in terms of high energy here, low energy here, or right to left. There's no rhyme or reason. You have to look at it. And how I do this is I always know that radio waves are low energy and X-ray are high energy. So there's low and there's high. Okay. And that will also help us when we talk about frequency, because this will be low frequency right here and high frequency. And for wavelength, now this is energy that I did right here at the beginning. Sorry, my writing's not great. Now for wavelength, this would be high, and this would be low. And we're going to practice all this stuff more. There we go. Okay, so let me clean this up a little bit so we can look at where infrared is and where visible and ultraviolet is. Infrared radiation has longer wavelength, lower frequency, and lower energy than visible light. That's a true statement. The visible region encompasses radiation of the intermediate frequency. It's kind of not super high, not super low. It's visible to the naked eye and takes on 7 distinct colors unless you're colorblind. Red, orange, yellow, green, blue, indigo, violet. And I always learn this as Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Next up in energy is the ultraviolet region, and that encompasses UV radiation, which has a shorter wavelength and therefore a higher frequency and energy than visible. So if we had to rank these, and this is a classic IB question, rank these high to low. We have visible, IR, and UV. Well, we would say that UV is greater than visible, which is greater than IR. Okay, there we go. We're moving right along, ladies and gentlemen. We talked a little bit in the previous slides about the relationship between frequency and wavelength. They have an inverse relationship. An inverse just means if one goes up, the other goes down. The product of the frequency multiplied by the wavelength of an electromagnetic wave is equal to the speed of light. So I'm repeating myself a little bit, but that's okay. That's a really powerful thing. For such a simple equation, what does it tell us? It says that if I know the wavelength, I can figure out the frequency. If I know the frequency, I can figure out the wavelength. This is a known quantity. It is a constant. It's 3.00 times 10 to the 8 meters per second. That's a speed, technically speaking, in a vacuum, because light will change speed depending on the medium that it's going through. And that's just like super important to all kinds of applications. When I was in the Navy and I was doing anti-submarine warfare, it really mattered what the temperature of the water a sound wave is going through. Light is the same thing, and that's why it separates in a prism into its distinct colors. I'm getting ahead of myself. Okay, we talked a little bit about this. This is the relationship between frequency and wavelength. Higher frequency, shorter wavelength. Lower frequency, longer wavelength. When white light passes through a prism, a continuous line is produced, right? So it's now separating into these distinct colors. The separation of white light into its component colors is known as dispersion. For something like a pure gas, like hydrogen, there's no spectrum. It's just it's a series of bright lines. And the thing that Bohr figured out, which I didn't do a great job a couple slides ago describing, the thing that he figured out is, you know what? The emission spectrum of hydrogen that you're looking at right now is identical to the absorption spectrum. And that told Bohr that, and it's beyond us how he figured that out, but he made the leap that it makes sense that if this is the case, these are exactly overlapping, that what's happening is in one, I'm going to go to the next slide here. I'm going to go back to here, sorry. When an electron is going down in energy to a lower energy level, and this would be 1 and this would be 2, it spits out energy in the form of light. Okay, well, when, and I apologize, I'm trying to get better with my drawing here, ladies and gentlemen. When an electron is sitting at its ground state and it gets hit by light, or you plug it into an electrical outlet, that electron is going to bump up. And so that's what you're seeing here. So this is causing absorption, and this is causing emission. That is a powerful, powerful idea. What do we need to know about this? We're going to talk about this some more when we get back into real live lectures. We need to know a little bit about what's happening to the electron when we see infrared, ultraviolet, or visible light. That's what we're responsible for. When you get to graduate school, you can figure out what's happening with radio waves, X-rays, and gamma rays. We just care right now about infrared, visible, and UV light. Okay, so let's make an observation here. Tie this all back to what we talked about. We said a while ago that the spacing between energy levels gets closer together as you get farther away from the nucleus. So in our picture here, this is kind of the nucleus right here, right? And this is the first energy level, the second, the third. Look at what's happening here. Okay. This is an emission spectrum for some atom. And as the electron is moving up, the amount of energy associated with it is telling you the color of light. So a couple of things we want to make an observation of here. Where is this electron starting from? These are all starting from the second energy level. And look, we're looking at the colors of the rainbow. So this is visible light that's being separated. This is emission. This means that the electron was at a higher energy level and it's falling down. Where is it falling down to? The second energy level. So whether it's emission, whether it's emission or absorption, when an electron leaves the second energy level or returns to the second energy level, we're talking about visible light. That's one thing that IB wants us to know. Electron transitions from n equals 2 to higher energy levels, like this, absorb energy that corresponds to a wavelength or frequency in the visible light. So you could, I'm going to try to draw here. I'm not a great artist, but I like to pretend that I am. This is our flashlight. It's just giving us visible light. When we shined visible light on an atom, it's going to push up electrons that are in the second energy level, not the first, not the third. Likewise, when we turn the flashlight off and those electrons lose their energy, they're going to fall back down to the second energy level and they're going to glow. So now when you see a firefly at night in the summertime and it glows, that's a chemical reaction that is pumping an electron up and it's falling back down to the second energy level inside that lightning bug. Nature's pretty cool. Okay, so this is a complicated looking diagram. The first time you look at it, we're going to keep breaking it down. IB chemistry wants you to know that anything falling down to the first energy level is UV radiation. We just saw that anything falling down to the second energy level was visible. And then lastly, anything falling down to the third energy level is infrared. We don't need to know about these other ones here. Okay, so infrared, ultraviolet, visible, infrared. 1, 2, 3. There we go. This is the hydrogen emission spectrum. And you can see here, this is all transitions down to the first energy level. So that's associated with UV light. These are our visible light, and we know it's visible light too because they're giving us these colors. And this would be infrared radiation down here. Pretty amazing, right? This is now you can see when we look at a Bohr model, why it's important to note that these energy levels get closer and closer together. And so we would say that an electron that should be down here, but for some reason makes its way up to here, we would call that an excited state. And then when it comes back down, it is relaxing. Okay. Let's answer a couple more questions and call it a wrap, folks. What is the electron configuration of chromium 2 plus? Oh, and I should have made these superscripts. Well, we need to find a periodic table. So while I'm doing that, I'm sure you guys have a periodic table handy right now. I'm going to bring one back. You'll always have a periodic table at your disposal. Let me copy that. And let me go back all the way to these questions. We always like to end with a review question or two. Here we go. Here's our periodic table. So whenever we're doing electron configuration, we need to count electrons. Chromium is right here. Ooh, that's one of those D block elements. And we learned that D block elements, they like to lose these here. So we would expect this to be, and we can do the shorthand notation. We know it's going to be argon. And then if it was just chromium, it would be argon 4s2 3d 1 2 3 1 2 3 4 5. Oh, wait a minute, excuse me, 1 2 3 4. But this is a +2, so it's lost 2 electrons. And these transition metals, they lose their 4s ones. So we would expect to see this. Right. And what we see here, nope, it's not this one. It's not this one. It's not this one. It's not this one. Excuse me. Sorry, I got a little bit excited here. There we go. That's what it is. The important thing to remember here is that transition metals lose D block electrons when forming ions, cations. Metals don't form anions. That's for another day. Here we go. Let's look at this one here. What is the relative atomic mass of an element with the following mass spectrum? Okay, so we know that relative atomic mass, which is given by that symbol, and is this number here, right? It's the number below the symbol. That is equal to the percent of the isotope right? But we have to add up all the percentages. And because this is a percentage, we're going to divide this by 100. Okay, so let's see. The math isn't that hard. So we have something at 23, and it looks like 80%. So we're going to say 80 times 23 divided by 100 plus 28 times 20. We're going to divide that by 100. And I need to find my periodic table. You guys are probably laughing at me now. I mean, my calculator. Because you probably can figure this out just by looking at it. We know it can't be, well, you know, I'm just going to have to do it, ladies and gentlemen. I apologize here for that. So we have, I need to clean this off, 0.8 times 23, all right, plus the quantity, 28 times, where's my times? 0.2, close paren. Yeah. Oh, it is 24. You know, my first thought was it's not 24, but then I thought, you know what, it kind of could be. We know that it couldn't be 27 because most of this is down here. You know that it probably couldn't be 26. You could quickly, if you didn't want to like figure this out, guess between these two. Okay, let's see. Which is correct for the following regions of the electromagnetic spectrum? Okay, ultraviolet, we know it's high energy, short wavelength. Infrared is low energy, low frequency. Yeah, let's see here. You know, I think it might be A, right? Because if it's high energy, it can't be low frequency. So that's not true. If it's high frequency, it could be short wavelength. Yep, that's true. High energy, long wavelength, that's not true. High frequency, long wavelength, no, that would not be true. So this is the correct statement here. Lastly, I think this is the last question. An ion has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Let's get our periodic table. We always want to count electrons. And that gives us a hint. Okay, it could be an ion. Let's see here. 2, 4, 10, 12, 18, 28. If it's a neutral atom and it's got 28 electrons, well, then it could be nickel. Nickel is not an option, right? We know it can't be the nickel ion because that would have 26 electrons. Copper plus 1, that has 28 electrons. That is looking like a good candidate. Copper plus 2, no, that's got 27. Cobalt, all the way down here, well, that would have 24. Yeah, so the answer is B. There we go. And let's see here. Oh, we got a couple more. All right, these are fun. The emission spectrum of hydrogen, emission. So in emission spectrum, we know that the electron has to be going up, not down. Of hydrogen, which electronic transition would produce a line in the visible spectrum, visible region, excuse me. It's got to be something going from the emission. Oh boy, excuse me guys. I just need to slow down. And I know some of you are out there going, wait a minute, Piety. When light is being emitted, it's falling in energy. And when it's being emitted in the visible spectrum, it's falling down to the second energy level. So which electronic transition would produce a visible region, would produce a line in the visible region of the electromagnetic spectrum? This one would produce emission in the ultraviolet. Can't be that one. This one would have produced emission in the visible, and that is what we're looking at because it's going down to the second energy level. This one would be absorption in the visible light. So this is absorption. not emission. And the key word there was emission. And this one would not be, this would be ultraviolet, whatever it is, it'd be ultraviolet absorption. There we go. How many electrons, excuse me, how many electrons does the ion phosphorus 3- contain? Well, phosphorus, the neutral atom, has 15. It's got 3 extra electrons, so it's going to have 18. And you guys probably remember from previous lessons that ions tend to have electron configurations with like 8, 10, 18 electrons. Yeah. How many protons, neutrons, electrons does the ion phosphorus 3+, this is phosphorus 27, have? Well, any phosphorus has 13 protons. That doesn't help us any here. You want to try to answer these questions before you look at the selected responses, because there's 3 distractors in there. And if you know what the answer is before you look at the distractors, you're going to be in a better situation. So we know that the protons equal 13, the neutrons equal 14, and I know that because 27 minus 13 is 14. And we just figured out that the number of electrons was 18. So we're looking for 13, 14, 18. 13, 14, 13, 13, 13, 14, 10. Wait a minute, what did I do wrong here? Oh. I know this is a bad question that we will fix. We just found a typo. This can't be phosphorus if it's 13. It has to be aluminum. So this would be correct if we went like this. So this should say aluminum 3+, 27, and 13. And that makes more sense because phosphorus doesn't typically form a positive ion. Okay. We'll save this one for another day, ladies and gentlemen. I hope you have enjoyed this lesson. I can't wait to talk. I'm so sorry. To talk more next week. Maybe what I'll do is I'll just have another session and we can just like hang out a little bit if you want. No pressure. We made it through chapter 2, topic 2. The people that attended the lessons and have looked at this stuff, that is awesome. If you're one of the people that didn't, for whatever reason, I'm not hating on you. We're going to get you covered. We're just going to have to pick it up when we come back. If you have a chance in the next couple of weeks, look at all these things. It's going to help you. I can't wait to see you face to face on a computer. Take care, guys. Enjoy the rest of your break. Email me with any questions as always, and do those Google Forms because you know what? We're going to Canvas. Bye.